Good afternoon, everyone. Welcome to the session Speed is Not All You Need for Data Processing by Kevin Ko and Wang.
I can go first. Maybe. Hello, everyone. Welcome to this non-hype talk. I know there are a lot of other interesting talks, but I really appreciate that you coming to this one. And today, Kevin and I are going to talk about why speed is not all you need for data processing. First of all, let me introduce myself and Kevin. My name is Han. I'm the head of Lift machine learning platform. I'm also the architect of Lift AI platform. Kevin Ko is the lead AI engineer at Drata. And both of us are the main contributors of this open source project Fugue. And Kevin is going to talk about the Fugue in his own section. Let's start. The data tooling landscape is exploding. So here is the compressed view of the main competitors in this field. In the small data, we have Pandas, Polars, DuckDB. In the big data, we have Spark, Dask, Ray, and Snowflake. In this field, the speed war is never ending. So let me ask you a question. How many people here have seen the speed benchmarks on social media? Just raise your hand. I see quite a lot. So the speed benchmarks is everywhere. Let me just pick one of the benchmarks that is well known. The H2O benchmark that was done in 2021. And this benchmark just used some predefined scenarios to test the speed of a couple of very popular computing frameworks and to compare the speed of them. And in 2023, DuckDB did this benchmark again with updated library. I know the font is small. Let me just extract some interesting number here. As you can see, from 2021 to 2023, the speed of Pandas, Polars, DuckDB, Spark, and Dask, they all improved significantly. And not surprisingly, DuckDB has the biggest performance improvement. It's almost 80 times. Right? And not surprisingly, DuckDB is the best among all in the 2023 version. Right? This is a mind-blowing number, and the improvement is amazing. Right? So now the question is, how can you, everyone here, how can you build the mind-blowing benchmarks by yourself? So here, I want to give you a very small training session to do that by yourself. Before doing that, let me ask you a very simple question. You have a bike, you have a supercar in this picture. And now think about that. How many people think the bike will be faster than the supercar? Please raise your hand. Okay, I see only one. Okay, so let me change this context a little bit. Assuming that you're competing on a busy road in Manhattan, how many people do you think the bike will be faster than the supercar? Yes, I see a lot. So what can we learn from this? It's very simple. The context matters in terms of any type of competition. And this is also how we can build our own mind-blowing benchmarks. It's very simple, 2 steps. The first step is just to think about a mind-blowing topic that is unexpected and so the second thing, after you have something that in your mind, you just need to tweak the context in order to find a benchmark that will prove your argument. That is so simple, right? So let's see some examples. So the first example is writing good pandas is all you need. Why? Because we don't want people to move to Polars or DuckDB. We just want people to keep using pandas. Right? How can we do that? Let's set up the context. I think there is something wrong with, oh, here, okay. Let's set up the context. Let's use the US accidents dataset on Kaggle. It contains 7 million rows and 46 columns. We want to test the filtering speed of Pandas. Filtering is a very common operation in Pandas, in data processing. And we want to find the rows with over 7 million. The ID is bigger than 7 million, and the distance is bigger than 10. And the data frame has also been loaded into memory. And looking at this column, the ID column, is in the format of A dash the number. So we need to do some data processing, the string processing, and then to compare with the threshold. Right? Okay, now let's just write the code. So let's directly translate that statement to this Pandas code. Even large language model can do this, no problem. Right? And with this translation, this execution takes over 3 seconds. Now in case 2, let's make it a little bit more interesting. Let's just change the order of the filtering and split them into 2 steps. The first step is just to filter on distance, and the second step is filter on ID. And this takes only 162 milliseconds, 20 times faster than the first case. What does that mean? The conclusion here is Pandas can be significantly faster if you write good code. But does good Pandas code equal to counterintuitive code? Is this a design flaw of Pandas that Pandas needs to fix it? I'm not sure. The second example, Polars. Now I want Polars to be the winner. I will compare Polars with Pandas and DuckDB. I will use the same context and do the same thing. So in case 1, just a direct translation into Polars and DuckDB expressions. We'll see that Polars is slightly faster than DuckDB. But now let's change the order of the filtering. You will see that now Polars takes only 15 milliseconds, and DuckDB's speed is not changed. So now you can see that Polars is over 5 times faster than DuckDB and 10 times faster than Pandas. Wow, amazing. So the conclusion is that Polars can be the fastest if you can write good Polars code. But think about that. The difference is 15 milliseconds. And you are processing millions of rows. For data practitioners, does 15 milliseconds really make a difference? Does that matter to you? And the second question, the I/O was not considered at all. So adding the I/O time for gigabytes of data, it can totally change the ranks. Right? So is Polars really faster? A lot faster? I'm not sure. Now let's talk about big data. Big data is dead. How many people have ever heard of this? Big data is dead. Please raise your hand. Yeah, cool. Yeah, big data is dead. That is a blog post that was written last year. It was saying that in a lot of cases, you just don't need big data. And you just need to use the small data tools to solve the problem. But as a big data practitioner, I'm not happy about this. Now I want to challenge it. I want to say big data is alive and kick-ass. Let's see how we solve this problem. Context. Again, context. Now I'm going to use a data frame with 10 columns. 3 billion rows, 100 gigabytes of Parquet data, so distributedly on S3. We want to take 1,000 samples of each group, grouped by column A, D, and G. Okay? And to solve this problem, we know that we just use the window function of SQL and take the top 1,000 rows of each group. Problem solved. Both DuckDB and Spark can do that. We will test the DuckDB on 32 and 64 CPUs. We will test the Spark on 32 to 1,024 CPUs. And the result is surprising. So for Spark, it works end-to-end. From even 32 CPUs, it works no problem. And at 1,024 CPUs, it's almost 10 times faster than 32 CPUs. And it can process 100 gigabytes of data under 1 minute, which is very amazing. But on the DuckDB side, it doesn't look good. It's all out of memory. 32 CPUs, 64 CPUs is out of memory. So what is the conclusion here? Spark is not only scalable, but also great, even using small amount of resources. DuckDB just can't keep up. But think about that. How common is this operation? Window operations. Like in SQL, you have select, you have join, you have union, you have group by. All those operations are way more common than this window functions. Is this representative enough to make this conclusion? I'm not sure. Let's take a look at the last example. The small data community is not happy about that blog post. Now, we want to fight back. Big data is alive and kick-ass until it dies again. How? How can I do that? Very simple. Context. How can I change the context? I just need to change one word. Instead of taking exactly 1,000 samples of each group, now I just take roughly 1,000 samples. Just that one word change will totally change how you compute. So now I no longer need to use window function. I just need to group by each group by and count, and then join back, multiply with a random number to see if that number is less than 1,000. That's how you sample the rough 1,000 samples. And we also test on the same set of CPUs. Result is stunning. You can see that for 32 and 64 CPUs, DuckDB are over 2 times faster than Spark. And comparing Spark at 1,024 CPUs and DuckDB at 64 CPUs, it's not much faster, but it will cost a lot. So here Spark is neither cost efficient nor fast compared to DuckDB. So what's the point to use Spark? If you can have a practical requirement for your business, and then Spark will be unnecessary. But again, think about that. You're processing 3 billion rows. Does the 1 minute difference really matter to you? Right? That's the absolute difference. That will make a real difference in terms of your own context, right? So if you have to do this every week, does that 1 minute make any difference to you? I'm not sure. So congratulations, you have finished this mini training session. And now you have learned how to write mind-blowing benchmarks. Or you have learned how to read mind-blowing benchmarks. Let's revisit the context of the H2O benchmark. You will see that the result is amazing, but I need to remind you a couple of the contexts. First, the 23 version used 3x CPUs and 2x memory. Second, all the things you compare in this benchmark should be compatible between SQL and Python, right? And then think about the scientific compute. Like, for example, the things that can be done by R, the statistical computing, they cannot be included in this type of competition because DuckDB cannot do that. Right? It cannot even do that. How can you compare the speed? Third, the file read and write times are not considered. I/O time are not considered in this case. Last but not the least, it is a single node benchmark, no matter for V1 or V2, and even for distributed engines. So is this even a fair comparison for Spark and Dask? Although this H2O benchmark is very comprehensive, I don't think it shows a full picture of the competition. So the British statistician George Box said, all models are wrong. Some are useful, right? I think all benchmarks are right because you design the context. You know it's right. But none of them are useful. Because the context, your context is not my context. No contexts are equal. Thank you. Now I will let Kevin to talk about the speed wars? Thank you.
So let's revisit why exactly are these vendors trying to push their benchmarks to us? And it's because they want us to convert to using their tool or their platform. And most especially, they want us to use their platform exclusively. And normally it's at the expense of us, the user. So let's take a look at late 2021 when this speed wars spilled over between Databricks and Snowflake. Databricks came out saying they did a benchmark. The text is small, but roughly Databricks said that they're performing 3 times faster than Snowflake, 12x better in price performance. So what did Snowflake do? They came back with a response. They said, Snowflake is not concerned about benchmarks that aren't grounded in the real world. They focus on the customer experience instead. But they provided a counter benchmark to discredit Databricks. And in the counter benchmark, they said that the effective cost of using Snowflake was 1/6 compared to what Databricks presented. So what did Databricks do? They also mentioned Databricks was lacking integrity in the benchmarks. So what did Databricks do? They came back and they said, the value of Databricks is actually that you can extend beyond the traditional SQL operations of a data warehouse, and you can augment those with R or Python code as well, and have and work on unstructured data in a data lake. But they discredited Snowflake's benchmark again, saying that they could not reproduce it. So lost in all of these benchmark wars is actually the fact that these tools are not mutually exclusive. And I've met a bunch of companies using these tools together. These tools are designed for different persona, where Snowflake is more geared towards data analysts, and Databricks is more geared for data scientists or people doing more machine learning work. And so we need to acknowledge that these tools are actually designed for different types of workloads. So when that article came out last year by Mother Duck saying big data is dead, there was actually a rebuttal article by Ponder. And Ponder said that even if you're a medium-sized company, number one, you still have big data. A lot of medium-sized companies still collect clickstream data or website usage data. And these are big data that tend to be underused and under-operationalized because people lack the tools in order to use them effectively. But we need to recognize that there are a couple of different buckets of workloads here. If you have a data pipeline, but it's non-urgent, it's big data, it's okay if it runs 1 hour. It's fine, it's non-urgent. But at the same time, maybe you want to run 10 or 20 machine learning models at the same time. And instead of running them sequentially, you want to run them in parallel. There are cases that demand us to use a distributed compute engine like Spark or Dask. And so the point here is that we need to be flexible in both being able to adjust compute and account for the data size. And we'll see this in this benchmark that was done by Coiled, a company that hosts Dask clusters. So this benchmark is actually going to be the topic of a talk right after this time slot, where they're going to go in more detail. But the study here was that they did a benchmark on 10 gig of data, 100 gig of data, 1 terabyte, 10 terabyte, etc. And they did a benchmark comparison against different tools. I won't go so deep into it, but the message here was that no tool was the best in all of those benchmarks, in all of those data scales. And that's pretty much what's expected, because Polars and DuckDB are designed to be on a single machine, and then you have Spark and Dask that are designed to be on a distributed cluster. So if you use Spark and Dask on the local machine, they're going to look bad. And similarly, if you try to use Polars and DuckDB at scale, then they're also going to look weaker compared to Spark and Dask. But let's think about this for a second. Because again, benchmarks follow the constraint of the interface. And if we're comparing SQL tools and Python tools side by side, that means we're constrained to only benchmarking SQL operations, like what Han mentioned. So we can't benchmark things like, for example, calculating the distribution of a column, or for example, doing like matrix operations. These things cannot be expressed in SQL, and that's why we need to use these tools alongside each other rather than treat them as mutually exclusive. But broader than that, lost in the discussion of speed, we fail to account for other things that are actually important for adopting tools. Number one, what does the ecosystem of the tool look like? And a lot of times people will say, Polars is faster than Pandas, but they really don't take into account the ecosystem that has been built around Pandas. Number two, developer experience. And this is something that's very unique to every organization. A lot of organizations tend to have people that are more versed in SQL than Python, and etc. A lot of people may not be so familiar with Spark and are really more versed in local compute. So the developer experience also really matters when choosing a tool, because we want to make sure that developers can be productive when working on data problems. Testability. Distributed compute tools tend to be less testable because in order to do an integration test, you need a cluster to test them. You also need to spin up the environment, etc. And then, but lastly, where tools like Polar, Pandas, and DuckDB fail is that they can't scale beyond a single machine. So when we have data or when we have compute needs that scale beyond what can be done in a single machine, then we need to graduate to some distributed compute framework like Spark or Dask. But first of all, let's ask: does speed actually matter? Because again, there's absolute time difference versus relative time difference, and a lot of times these benchmarks will say 10x faster, right? What does 10x faster mean? Are we going from 1 hour to 6 minutes, or are we going from 6 minutes to 30 seconds? And the vast majority of pipelines are not at the 1 hour scale or 2 hour scale. Some can be, but it will normally be a minority of pipelines. Number two, instead of trying to change framework immediately and go from Pandas to Polars, we need to ask first if we can optimize the code. Can we just tweak some lines of code in order to avoid a full refactor of moving on to Polars? And number three, lost in this discussion also, is the fact that the total cost of a data project is both developer cost and infrastructure cost. And a lot of times, we try to over-optimize on the infrastructure costs at the expense of developer cost. So instead of falling into this trap of having to choose a tool, how do we actually avoid choosing and use these tools as more of a tool belt where we can just combine them together in order to use the strengths and the strengths of multiple tools together? And with that, I have a scenario here. So I faced this 2 jobs ago, actually. So I was a data scientist responsible for making an internal library. This internal library would hold a lot of business logic, very custom business logic. A lot of like, if this value is this, then that, and then chaining if else's. So we have this very custom business logic, and it's going to be used by other data scientists in the company. Some of the around 90% of the projects are small data, Pandas, Polars. 10% of the projects are in Spark. So the question becomes, number one, do I write this library in a local engine like Polars or DuckDB? Number two, do I write it in Spark? Or number three, do I write 2 implementations of the same business logic, one for Polars and one for Spark? And I want to ask the audiences, so who here would, number one, use a local engine to write this business logic? I see a few hands. Number two, who would use Spark to write this business logic, a big data framework? I still see a few hands. Or number three, who would create 2 implementations, one in the local engine and one in Spark? I see a few hands. And I think overall, there are not a lot of hands raised because this is a hard question. There's no good answer. If I use a local engine to write, like Polars or DuckDB, then the problem is the people who are using big data projects can't leverage that package. If I write it in Spark, then that means that all the small data projects now have to be in Spark, which is what some shops do. They say, hey, since we have big pipelines, we just decide to have everything written in Spark so we can reuse the same code all throughout. And writing it in both is also not a good option because now I have to change that business logic in two places, right? And so that's where abstraction layers come in. Is it possible to define the code once in the grammar that we prefer, in an environment that we're comfortable in, and then when we're ready to scale it to the distributed engines, is there some way to port pandas, the small data code over to big data seamlessly? And that's where Fugue comes in, the project that we're working on. So Fugue is an abstraction layer. It's not the only abstraction layer. There's a lot more out there. But what these abstraction layers do is they try to unify the code so that you only have to, for example, write it in pandas, and then we bring it over to Spark, Dask, Array for you. So now with this setup, what we can do is we can write that internal library on local compute, and in those 10% cases where it needs to go to Spark, we just port it over through the abstraction layer. And the abstraction layer gives us the best of both worlds. We can combine local developer experience, local testability, with a distributed scalable infrastructure. And this is an example of using multiple tools in conjunction together to get the best of both worlds. And a lot of pushback is around how combining more tools can lead to more maintenance. And we're here to provide an example that that's not the case. So here is a traditional Spark SQL query. It's doing a rolling z-score over some data and some filtering. But this is a very common example. This is actually a shorter Spark SQL query, and they tend to balloon in size also, as with any SQL. Number two is, I don't know if you can see, oh, there. In the highlighted yellow, there's actually special Spark syntax also. So now this same Spark SQL query can't be used, even if SQL tends to be scale agnostic, there's still some special syntax here that prevents this from being used with local engines like DuckDB. Another thing is we use this table Z multiple times. And if you're familiar with distributed compute, if any table is reused, then you need to persist it so that it's not computed twice because of the lazy evaluation. And SQL doesn't provide the grammar in order to perform all the operations of a distributed framework. So that's a weakness of SQL. And so this is what Fugue SQL looks like. Fugue is both Python and SQL. Here I'm just going to show the SQL interface. But here we have a fully engine agnostic representation of our logic. This same code will work on DuckDB and will work on Spark SQL or Dask SQL. And in order to allow SQL to be the grammar for end-to-end computation, we added keywords like load and save to SQL also. We also added keywords like persist highlighted there that lets you fully use the underlying execution engine. So a very common problem of abstraction layers is that you don't have full access to the capabilities of Spark or Dask, and so we have to expose them on this Fugue SQL. And then we have variable assignment as well for data frames. But that code that I showed can actually be better. So can we combine Python and SQL together to achieve the same use case? So here I have a plain Python function. There's nothing special about it aside from the comment at the top that the Python function takes pandas data frame in, it takes pandas data frame out. This code can be tested. It will work on pandas, and the question is how can we bring this to Spark? And so in Fugue SQL, we added keywords like transform and prepartition so that you can use SQL and Python together. So here, SQL is the first class interface, and now it's invoking this Python function. And look at the number of lines of code here. It's significantly less than what we had earlier, where we had longer SQL queries. And so we actually have less lines of code. And if these slides look familiar to you, we actually presented the same slides 2 years ago in PyCon 2022, but we had a very different mentality. We showed a benchmark, and we showed everyone how Fugue SQL was actually faster than using Spark SQL directly. But today, we're here to tell you that don't trust this benchmark, and probably do a benchmark for yourself. So in conclusion, we want to say speed is not all you need. And we have to focus on the full package of developer productivity, testability, and scalability. And one way to get the best of both worlds, of Python and SQL, of small data engines and big data engines, is to consider abstraction layers that decouple the execution from the underlying the logic from the underlying execution. Thank you. We're out of time, so if anyone wants to chat, we'll be outside for questions. Thank you, everyone.
Thank you.